Right, so this is lecture number 11. Let's settle down quickly. Today we'll start with a new topic on Fortran. So this is going to be an introduction to Fortran. So we have completed discussion on HPC now. We'll take it up again when we start, when we talk about Param Himalaya. But I thought that there's enough of HPC for 3 lectures now. So let's move on to Fortran so that we learn how to write some heavy duty codes and then we can start using them on the supercomputer. So the agenda for today is going to be a discussion on compiled languages, and in particular, particularly Fortran 90 that we'll talk about. I'll talk about some syntax, some basic syntax of Fortran 90. Now we'll assume that you know how to program because you already have done a significant bit of scientific computing in Python by now. So we'll talk about declaring variables, loops, some data types like Boolean. We'll have a lab practice session. So what I've done is whatever codes I am going to discuss in the class today, those have been pushed to the repository. So you can pull them right now or later, and this time I strongly suggest that you practice whatever codes we discuss, whatever we do in the class, try to complete that in today's lab. And then towards the last 15-20 minutes, I'll talk about debugging in Python through a demo. So let's get into it. So let's talk about compiled versus interpreted languages. So till now we've talked about Python, and Python is an interpreted language. So what we did was, for example, in IPython, we used to type in a command, a line, and then press enter and it gets executed. So what happens under the hood is that each line of code is converted to some sort of a low level machine language code. When we type something and press enter. So there's an interpreter that interprets our high level language, so to say, that we are typing, and converts that to something called a machine code or a machine level code. So let's say if we say z equals x plus y. So for us it's a very simple statement, but for the computer it has to do a lot of operations to execute this z equals x plus y. So all that happens through this interpreter. It will interpret what you are trying to do, find out the values of x and y, I mean locate where x and y are stored in the memory, and then take them out of there, take them to something called registers, which are faster, which is a faster memory available close to the CPU, and then it has to send them to adders so that it can add x and y, and the result that is generated, which is also stored on the register, is then transported back or transferred to the memory, and then whatever you want to do with it is done. So there's a lot of steps involved in this single statement, but all that is done under the hood through the interpreter. Even the instruction that we write is also stored somewhere in the form of a binary code. Now, if we compare that with a compiled language, in compiled language we tend to, we actually send the whole code for compilation. So the compiler is going to see the complete code, not just one line, for example, z equals x plus y, but everything before and after that is going to be seen by the compiler at once, and then it will figure out what is the best way to execute them. It won't execute it, it will just compile into an executable. It will only execute when you run it, but the complete plan as to how it will execute is developed in the form of a machine language code. So it also has to figure out and do some sort of optimizations so that the resultant executable is going to do the same thing that you are intending, but in a more effective manner. So that is the job of a compiler. So it's not just one line, but many lines together, and has to understand the interrelationship between one and the others. So this compiler's job is actually quite complicated, but they exist and they make our lives easier by we only have to focus on the algorithm, and how to execute it most effectively is taken care of by the compiler to some extent. I mean, of course, programmer has to understand how to write the most optimized code as well, if you want to write faster codes, but the compiler takes a lot of responsibility in that aspect. So one drawback of Python, MATLAB or other interpreted languages is that it cannot optimize over the entire program, because it doesn't even know what you're going to write after this line. So it runs one line at a time. So it cannot optimize based on the complete program, and we'll see later what sort of optimizations are carried out in such situations. Okay, so whenever we deal with a compiled language, which is always expected to be faster than interpreted languages, we have to develop a source code, a code. It looks like a Python script, but it can exist in many different files, same as Python project. And I mean, the compiler expects an input as all those files that you tend to convert to an executable. It will analyze the code and then it will convert to something called an object code. So what happens is, let's say one particular Fortran file that you're dealing with, which has the main program. So the compiler will try to understand this high level code, convert that to a machine code in the form of an object code. So in Fortran, the compilation process results in something like a .o file, an object file. Okay, and then every Fortran code, every file that you supply to the compiler is going to get converted to a corresponding object code, a .o file. In some cases, some languages, there is a .obj file. I mean, that's the object file that is generated. I'll talk more about it as we go along. So then this object code or a collection of object codes are passed to something called a linker. And the linker's job, as the name suggests, is to link those object codes together and make into an executable. Okay. So why is a compiler working in two steps? That's an obvious question that comes to mind. Why not just one step to compile and then give us an executable? Again, as we'll see later, that typical scientific computing projects are going to be huge, in the sense that let's talk about mathematics, differentiation library. So you'll want to have differentiation which can be of either let's say, let's say integration. So integration can be indefinite or definite. Okay. And then in the indefinite, you'll have different types of function that you want to deal with. In definite, you'll want to have different, let's say, methods, that numerical methods that you want to use to integrate the function in a definite sense. So what happens is that you tend to have different functions which are sitting in different files, and they don't have much to do with the other functions which are solving the problem differently. So then we keep them separate, we compile them separately into different object files, and whenever we want to create an executable that will ultimately run, we'll have to link them together. Now if you, let's say, change one particular function or you implement a new method, there's no point, there's no need to compile all other parts of the code which are independent. So that way what happens is that you don't spend a lot of time, compilation time, on compiling the complete code. You only compile the part that you have developed separately, and then the linker, because whatever function you have developed, it may be calling some other function. It's not changing anything, it's calling a function, or the function that you have developed is being called in a main function somewhere else. So that way the linker will link these function calls and variable calls to each other. So the object files typically will have some functions or variables sitting, and then the linker will connect them together into one executable. It's a very hand-wavy way of explaining this concept. So as I said that large programs will have many files. You don't want to waste resources on compiling everything, and compilation actually can take a lot of time. So you only recompile whatever's changed, and then you link everything together. So we'll discuss this in more detail when we talk about makefiles, which is an amazing concept that is used to make executables from projects. Okay, so it manages dependencies very effectively. Well, history of Fortran has been there for a very long time, since 1950s, And 50s, by the way, in computing chronology, it's very old, archaic, 1950. I mean, uh, there's been a significant change in the way computers work and we program from 1950 to 2024. So it's a very old language. It actually translates to formula translator. That's what Fortran means. So it was developed particularly for scientific computing, for implementing mathematical formulas and so on. Unlike languages like C or C++, which by their default nature is not developed for scientific computing. So you have to import the right kind of modules or libraries to make sure that they behave as expected. But Fortran has many operations like matrix multiplication and so on built into its core. So for scientific computing, it is a very rich language in that sense. So before Fortran, everything was in assembly language or machine code. I'm not sure. Is there anyone who has actually coded in assembly language? Just one. Okay. It's difficult. It's very different, especially from the way you write high level languages. Okay. You have to understand how the hardware is working to be able to write assembly language or machine code. Of course, I mean that can be much faster. So if you want to do something related to, let's say, banking, where the time of a transaction is actually quite important, let's say investment banking and all. So there you might want to code very close to the hardware. So there these things still work, but otherwise for every other application you will tend to work with higher level languages so that you can do more complex things as humans. So earlier, before Fortran, things were written in machine code or assembly languages. So they were quite complicated to work with. So Fortran was the first high-level language at that time, which could do operations like x plus y and so on, and then do it many times so that you could program computers in the way you wanted. And again, with Fortran, we don't have to worry about how to store the information in memory, how to bring that into, let's say, your cache or registers, how to do some operations on that. So that again is handled by the compiler. Unlike the older machine codes where you had to figure out these things yourself. So Fortran in 1950s, then Fortran 1, 2, 3, 4, 66, and then major changes happened in Fortran 77, called Fortran 77. Okay, so F77 is still used. In fact, you will see some legacy codes which are still being used nowadays, because you see that these are very huge codes, scientific computing codes, and nobody has the patience and the time to sit and rewrite it. And especially since it was written in Fortran 77, which was not as high level language as the one that exists today. So it could be, in fact, some of the codes are faster in Fortran 77 the way they were written earlier as compared to the same algorithms if they were translated to Fortran 90 or 95 or even 2003. So what that means is that nobody wants to touch it for different reasons, but they are fast. Okay. So they are still very fast and powerful for scientific computing, these codes. So you may, I mean, if you work with scientific computing, you may still encounter these Fortran 77 codes. So there's a quote which says that, that was again given in 80s, that I don't know what the language of year Y2000 will be, but it will look like Fortran. So the idea was that Fortran, I mean the whole gist of this quote is that Fortran will still be there for scientific computing, and it is still there. You still, I mean, in my PhD, which happened a couple of years ago, I was working on a Fortran based code, which is doing state of the art things nowadays in terms of fluid mechanics. So it's still there. Okay. So after 77, the next major change happened in 1990. So it's called Fortran 90 or F90. And then some minor changes happened in 95, which was called Fortran 95. And then 2003 and 2008, some more changes were implemented. But many compilers still haven't implemented these 2003 or 2008 changes of Fortran. So in this course, we'll work with a compiler called gfortran, which is a GNU-based free compiler available for Fortran, and we'll be using Fortran 90. So our files will look like, for example, example1.f90. So F90 tells us that it is a Fortran code written for, it's a code written in Fortran, which is suitable for Fortran 90 compiler. Several commercial compilers are also available, for example, Intel Fortran. So remember, the compiler's job is to convert your code to a code that can run fast on a hardware, on a particular hardware. So if you are using an Intel based machine or an Intel based cluster or an Intel based supercomputer, then if you use an Intel based compiler, then that compiler is optimized to convert your Fortran code to a code that will run fast on that hardware. So every hardware is different. If you buy an AMD based machine versus an Intel based machine, or a Mac based, M1 or M3, whatever is available nowadays, this Apple Silicon based machine. So they'll all have different hardware. So there has to be some sort of a compiler that can understand the hardware and convert, and also understand the programming language you are using to convert your code to a machine code on that hardware. Okay, so G Fortran is general purpose, so it may not be the fastest, but it is more versatile. And for this particular course or for most exercises, it's still okay. But if you really want to do heavy duty work, then you must compile your code with a compiler that is shipped by the hardware provider. Okay, so Intel Fortran called iFort is optimized for Intel architecture, and that's available. I think that's not free for students. It used to be free earlier. I'm not sure what the case is now. But if you're working with heavy duty machines, typically those cloud based services or hardware providers will provide you access to those Intel based compilers as well if you're using an Intel based cluster. So we use Intel Xeon machines on the HPC cluster that we have. So this I've already talked about legacy codes. So codes which were written long ago, which have millions of lines, nobody wants to rewrite them. So we're still using those legacy codes. So Fortran 77 is still very much there. So it makes sense to understand some ideas of Fortran 77 as well if you want to stay with the language. A general note here that if you add many high level features to a language, like you have in Python, for example, then it becomes easier for us as humans, but for compilers it becomes difficult because we don't talk the same language as computers do. So for the compilers to optimize this into the fastest possible code, it becomes difficult. Okay, so as I said, that there's always a trade-off between our comfort and the speed with which it will run on a machine. If we're talking about languages like Fortran, so we have to either use ideas from older Fortran ideas which allow us a stricter control over the memory management and how the information moves, if you really want to make things run, if every microsecond matters for you. Okay. Otherwise, these free GNU based compilers are good enough. So one concept, for example, is pointers. So pointers are available in C. So they are basically they point to a certain memory location, but that memory location where a pointer is pointing to it could be anything. Okay, so it could be an integer, it could be a float, it could be some other object from some other class, and so on. So compilers may not know what the pointer is pointing to in many cases, but in Fortran they don't even exist. So that ways what happens is that the compiler knows beforehand what is the type of every every data type is known by Fortran. So the compiler can do a better job. Okay, so these are some ideas which make Fortran faster in certain sense. But again, with pointers you can do many interesting things in data structures. So those features then are not available to a Fortran user. So it's not a general purpose language in that sense, but scientific computing people tend to prefer it to some extent. Right, so some older ideas. So this, what you look at, is a punched card. Okay. I'm sure nobody has used that. This existed long ago. So Fortran 77 for example, was implemented on a punch card. Now we have hard drives where we can store things, but this is how information was, this is how codes were written. You would have a physical card, and then you would, on the top, I'm not sure if you can see that, it says Z of 1 equals y plus w of 1. Okay, so this is basically a statement, a line in a code. Z equals, let's say, y plus w. So this whole card is simply implementing this line Z equals y plus w. So it's converting that Z bracket 1. So every character Z, for example, on an ASCII way, you can have a code for Z. So this first line is basically a code for the letter Z. Second line is for a bracket. Then the third line is for 1. The fourth line is for bracket close, and so on. So this is one line or line implemented on a punch card, and you can imagine that if you have 100 lines, then you have 100 cards like this. So people used to feed them, and then there's a mechanical device that would read the hole on the punch and then convert that to statement, and then that will then work in the computer. So this is how you would feed information to a computer. So in 77, Fortran 77 was a fixed format because you have a fixed size of a card. So that way is there's the first few characters which are used, which are basically, I think it was, I've never used these cards. I think it was line number. And then executable statements would always start from column 7 on, or later. And then towards the end, you had some characters again fixed for, I think, storing some number to organize cards. Because you'll want to organize cards. If you throw them all on the ground, then it becomes a big problem as to how to organize them. So with this last few characters in the card, you could use that information to organize it. That's pretty much what I know. So first 6 for statement labels, and the last 6 or 7 for organizing the cards. And executable statement exists, will only be written between columns 7 all the way to column 60 something. So this is how a box of cards is organized. So smart people would draw a slant line so that if you want to organize them again, you can organize them more conveniently. So the card readers that would read these cards would have mechanical rate of reading, let's say 1000 cards per minute, and then take some time to enter that program into a computer, and then the code would run for many hours, and then the result would be printed on a sheet of paper, like a dot matrix, like that. So it will get printed. So you will wait for 15 hours, 5 hours to load the information onto the computer, then 10 hours to run, and then a few hours to print, and the printout would say that error on line number 3, right? And then you figure out what the problem was, and then you remake the cards, put them in the right order, feed them again. So you see that if you get impatient, if you get an error, and then you really want to you get frustrated with those errors, imagine how computing was in 70s. So we have moved a long way since then. Well, even before that, there was something called a paper tape before these cards. So the whole code was written on this tape, and if you make one mistake, you have to start punching the whole tape again. This was before cards. I mean, this depends on what sort of mechanical devices could read these programs. So don't get frustrated with programming nowadays. Right, so getting back to more implementable things. So file extension for Fortran 77 codes, which are fixed format codes. So even nowadays, if you read a code Fortran 77, you will see that it indents the code and starts from a certain line, because that code till line number 6, character number 6 cannot be read. It is not used for executable statement, and you cannot go on writing the line to make sure that you finish before a certain correct number of characters, because it will only have those many characters available to read. So .f files, if you see them, they are typically F7 Fortran 77 codes. So G Fortran can compile both Fortran 77 and Fortran 90. So in Fortran 90 is free format, so you can start from any line, any character, you can end at any character. So we'll be using Fortran 90. So indentation is optional in Fortran, unlike Python, where it has a meaning, but it is still highly recommended you indent your code for readability purposes for yourself as well as others. Right, so let's jump into it. Let's look at a few examples on Fortran codes. So this is a very simple Fortran code called example 1.f90. It's already been pushed onto the codes repo on GitHub. So let's look at how a code looks. So this is an exclamation would stand for a comment, like hash in Python is an exclamation in Fortran. Anything after an exclamation sign will be ignored by the compiler. So the program always starts with this line called program space the name of the program, example 1 in this case, and then the last line in the program will be end program, name of the program, which is example 1. Then you would have a certain number of lines. You can see that we are indenting it to just for readability purposes, that everything that is indented is a part of this program, but again that is not necessary but highly recommended. And then in Fortran, like every other compiled language, you will first declare variables and then you will have executable statements. So by declaration we means that you will just tell the compiler that you have variables x, y and z which are of the type real. Okay, so real is a type like real number. So as I said, it was developed by mathematicians for mathematics operations. So it uses real, unlike you have the word float or a double in other languages. So real is a real number, and kind equal to 8 means it is 8 byte. That means it is using 8 times 8, 64 bits to represent this real number. So it's using the IEEE 754 standard, but you can also have kind equal to 4. So that will use 8 times 4, 32 bits to represent the real number. Okay, so some digits will be, so one will be fixed for a sign as we discussed earlier, and then a few of them will be fixed for the mantissa and a few for the exponent. Okay, I'll talk about this implicit none in a few minutes. So x, y and z are variables, so we have declared them, and then after that you have these statements where you tend to do something with these variables. Okay, so you define the values of x and y, and then you say z is equal to x plus y, you print the value of z, and that's the end of the program. So I've talked about kind equal to 8 means 8 bytes for storage. So let's look at this line where we are defining the value of x. So we say x equals 3.d0. Okay, so that basically means it's 3.0, and the reason we have put a d here is it's a double precision, so 8 bytes. So x, yes, x is an 8 byte real number, but you are making it equal to something. So when you write 3.d0, then the computer represents this number 3.0 in an 8 byte representation and puts that into x. So if I had written 3.e0, x equal to 3.e0, then it will use a single precision representation for this number and put that into x, which would then convert it to a double precision, however it does. But if you want a double precision number, then you have to use 3.d0. If you want to use a single precision number, you use 3.e0. So e0 would mean a 4 byte representation of 3.0. Okay, and then y is equal to 1.d minus 1. So this equals to 1.0 into 10 to the power of minus 1. So this is just a representation. So this 1 point means 1 point, and then 0, and then d means it's a double precision, and then the minus 1 means that's an exponent of that. So this 3.d0 was 3.0 into 10 raised to the power 0, which is 3.0. So this is 0.1. So once you have it says 2.d minus 1, so I think there's some typing mistake here. So y should be 2.d minus 1, so that is 0.2. Is that clear? So I'll move a bit slow because I'll move a little slow now, sorry, a little faster now as compared to what we did in Python, because I would want you to figure out things by yourself when you start reading and running the codes in the lab session, and then we can discuss more if needed. So then let's look at the print statement. So print followed by a star. So star means it's a free format. So I am not specifying how the number z would be formatted. However the computer wants, it can format. So like we do in Python, right? We used to say that print and then some variable. So without specifying the formatting, so it will figure out what's the best way to represent that on the screen. So this star means that, and then comma is just for separating this star, and then we say z equal to, so that is in double quotes, that's a string, and then followed by z. So you separate a string with the variables through a comma. So it will print z equal to space, and then it will put the value of z whatever it is. So in this case it is 3.2. So we'll run and see what it results in. So we'll see also later that how to specify a particular format like we did in Python. So we said these many digits after the decimal, these many digits in total, and so on. So we can do that in Fortran as well. Right. So once we understand the code and the code's ready, the next thing is to compile it. So the way you compile this code is on the terminal. If you are in the same folder where the code exists, you type gfortran, that's the Fortran compiler, space, and then the name of the Fortran file, which is example1.f90. So in this, what happens is compilation and linking, these two steps happen at the same, they happen one after the other together, and you get a resultant executable. And the executable, default executable name will be a.out. Like you have in Windows, you have something .exe. So here you will have a.out as the default name. You can change it if you want. For I don't know why, for some historical reasons it is a.out. There's no particular reason why it's a.out logically. And then once you have the executable prepared, next you have to run it. So the way you run this executable is you type, you can, in some cases you can simply say a.out enter, it will run it. In some cases you have to use a /. So remember // refers to the current directory, right? So dot refers to the current directory, dot refers to the directory above. So if you write a // that basically means current directory, but that also gives some hint to the shell that you are trying to run an executable. So you use a // followed by a.out, so that runs the executable, and then it prints z equal to followed by the value of z. Okay. Now this a.out was compiled on a particular hardware, like I compile on my hardware. So if I would not give you that a.out to run yourself, you would typically compile the code yourself, and your compiler will try to figure out what hardware you have and generate an executable. If I give that executable to you, in most cases it will have some problems at some stage or the other. If you have an exactly same hardware, then yes, it will be fine, but otherwise it's always recommended you always compile the code on your hardware and then use it. You'll see that some cases the codes will, the program will be provided with an executable which is portable, which is good, but that won't be most optimized. If you really want to do scientific computing, get the source code, compile it, and then it may take some time to compile. You may have to figure out how to compile, get all the libraries and so on, but that's worth it if you want to, if your code is expected to run for days or months for your work or research. Okay. So let's look at the two-step process where you compile it first, generate an object file, and then you link it to an executable. Well, let's look at first if I want to change that a.out to something else, because it's very confusing. Because if you run if you compile three different codes, you expect to have three different executables, but all of them are a.out, is very confusing as to which one you're running. So if you simply say gfortran example1.f90, and this time we say -o flag, which basically says that I want to rename my output file, and the output file name is example1.exe. So this time instead of a.out, it will generate example1.exe, and you run it the same way /example1.exe. So that gives the same result. Now let's look at how to separate the compilation and the linking steps, because as I said that in bigger projects you have hundreds of thousands of codes and you don't want to recompile everything every time. So we say gfortran space minus c. So this minus c is telling that I only want to compile it, and then you give the code name, and then it generates something called example1.o, and you cannot run it as of now. Then you have to supply that example1.o to gfortran, and then you give a minus o, which is optional, and you give an executable name. If you don't give it, it will generate a.out again. Sorry. Okay, so when the gfortran compiler sees an .o file, it knows it has to link it. Now in this case, is only one file, so there's nothing much to do. It just generates an executable. If I had 3 different files, and very soon in the next lecture we'll see how to write Fortran modules and so on, so that we start having codes which is split into different files. So you'll see that we can just compile one of them which is changed and then link them all together again. Okay, so .o file that is generated here, it is an object file, and as I said, it has some linking to be done. It has some symbols which it has to resolve, and what we'll see later is that if you have, it has a function call, then the function is defined in a separate Fortran file, which is a separate .o file after compiling. Then once you link them together, those function calls and those symbols will be resolved into the executable. So linker's job is also very important to link it, and sometimes it uses a static linking or dynamic linking. You'll hear these words. So static linking is that basically if you have a library, it will pull the code from the library and it will put that into your compile and put that into your executable. Whereas dynamic is that it will depend on the executable on the library. So when you run the code, at that time it will call the library and for some calls. So you may hear these words called static or dynamic linking. So this is what it means. And sometimes linker also does some optimization where it may reorder your code to do some generate an executable which is more efficient, but that's rare. So let's see if there's an error. How does the compiler behave in Fortran? So here what we have done is, well, let's talk about implicit none before that. So this, you see this line called implicit none. Now when Fortran was written, I mean we also do that, we have some variables we tend to use for integers and some variables we tend to use for real numbers. So this x, y, z, and I think there is a rule, I don't remember that, but z typically would refer to a real number. I think I, j, k refers to integers, and then x, y, z all refers to real numbers. Implicitly, you don't even have to declare them, but that's very confusing. I mean, why should I remember whether I is supposed to be an integer? I would want in some cases I to be a real number. So what you do is you write implicit none. So what that tells the compiler is that you are not depending on implicit data types. You will explicitly specify what is the type of a given variable. Okay, so that implicit dependence is gone. So that makes things more predictable. So it's an always you will see an implicit none written on the top of a Fortran code. So let's say we introduce an error. We instead of z we say z equals x plus y, and you now compile this file. You'll get an error which says error. So it puts a 1 here. Says symbol zz at 1, which is here, has no implicit type, because you have said implicit none, so there is no implicit type available for zz, and it throws an error. But on the other hand, if we remove the implicit none statement And now we run this erroneous code again, in the sense that we are saying z equals x plus y, and now we are printing z. It will actually compile, and when you run it, it will give some rubbish value for z. Again, we'll see that today when I do a demo for the code, and then I'll let you try things out yourself. So what's happening here is that it says z equals x plus y, but now implicit none is gone. So the implicitly, if any variable starts with z, it is a real number. So it assigns a value, a memory allocation to zz, and that is equal to x plus y, but you actually print z. And z was declared, but it was never given a value. So whatever the default value of the compiler has given, or whatever, I mean, it's been given some memory location, some bits. So whatever those bits were when it was given that location, and the bits could be either 0 or 1, whatever it is. It has not reset those bits. So whatever those bits are, it will convert that to a real number based on this IEEE 754 standard, and it will give you the value, which is a random nonsense, right? Because it's not what you expect to print. So that's the whole idea, that make sure you include implicit none, so that you don't. It's very difficult sometimes to pick these errors. You will spend hours and you realize that, oh, not written implicit none on the top. So be careful. Okay, so here's that slide where we have the implicit representation. So integers are I, j, k, l, m, n, or any variable that starts with these letters is going to be given a default type of integer if you do not include implicit none. And real numbers are actually 4 byte unless you give it a double precision, and anything else that is anything other than I to n is going to be a real number. But again, it's an older convention. It's always safe to include implicit none on the top for clarity. But you know, people still use these, I mean, they try to preserve these rules. They try to use I, j, k, l, m, n for integers, and they try to use others for, I mean, some people do that. They still preserve the old rules, even though they have implicit none on the top. But again, that is not important. Now here's a Fortran code that let me take you through a couple of codes, and then we'll run them, and then you can try it out yourself, or you can run them while I'm demonstrating things. So here you have a loop. So this is to demonstrate the idea of looping, a for loop, or a do loop in this case, in Fortran, as well as demonstrating the use of arrays. So let's go line by line. So we have a comment in the top, just the code name. Then we say program loop 1, that's the beginning of the program. Everything inside this program and end program is going to be the executable. Then you have implicit none. So just to be safe, we say integer n equal to 10,000, but it also says parameter. Okay, so parameter is used for variables which will never change, like constants. So n is a constant. So that way is, if by mistake you try to change the value of n, I mean, you forget that n was 10,000 for some reason, and you try to declare a new variable called n, it will throw an error. So for constants, you specify the value, you declare and define them at the same place. You say integer, comma, parameter, it's a parameter like the name suggests, it's a constant, and the value is 10,000. Next you have real numbers. Kind equal to 8, so 8 byte reals, that's a double precision. And then with a comma you say dimension, and then you give the value of n. So that means it's a vector of dimension 10,000, and then double colon means that now follows the variables x comma y. So x and y, I have declared them in the same line. So x is also an array of size 10,000, and y is also an array of size 10,000. Okay, so the dimension of x is 10,000 and the dimension of y is 10,000. And then we have an integer, just I as an integer. So then we have this do and end do. Okay. Now in Python you had a for loop. You'll start it and then you'll never end it, because indentation will tell you what is part of a for loop. But here you have to actually explicitly specify end do. So whatever comes between do and end do is a part of this loop. So if I say do I equal to 1 to n, so I will go from 1 to n, start from 1 and go till n in steps of 1 by default, and then I say x of I. So unlike Python, you had square brackets, you have curly here, you have parentheses here. You say x of I equals 3.d0, that means 3.0 into I. So that means x of 1 will become 3 times 1, x of 2 will become 6, x of 3 will become 9, and so on. So you are basically defining this array and putting some values into it. Similarly, the other do loop is going to define the value of y, but this time we are saying y of I is equal to 2 times x of I, and x of I was 3 times I, so that becomes 6 times I in this case. This is a dummy code just to give you some experience. So when you start running this code, just play around with it. If a question comes to you that what happens if I make it 3.e0, rather than asking me, why don't you run it yourself and see what happens? Okay, just play around with these ideas, these codes, and learn more about Fortran through that. And then finally we print something. So we say print star some string last y computed, and then we print the value of y of n. So n is 10,000, so it only prints the last value of the array of y. So y of 10,000. And you see here that indexing starts from 1 in Fortran, unlike Python where it starts from 0. Questions?
So can we also specify dimension n cross n or n cross n?
You can, yeah, you can. So we'll see that in the next lecture. Okay, so parameter, as I said, is going to be a constant. It will not change. And you see, why are we doing this? One is that it prevents us from making a mistake of using or changing n later in the program. The other thing is that it also tells the compiler some more information. It tells the compiler that n is a constant. It is not going to change. So compiler can do some more optimizations based on that. It's always good to. I could have made the code without the parameter word here. It would still run fine. But if you put the word parameter, it may help the compiler to do some optimizations, and your resultant executable may be slightly faster. And dimension of n, as we saw that it makes x and y as arrays of length n. So x of I means the ith element of the array ix. And well, let's talk about it. So we used do and end do, and everything in between that is going to be a part of this loop. In the older Fortran way, we remember that the first 6 Fortran 77, the first 6 characters were fixed for some statement label. So this was the kind of label that people used to give. So they'll say do, then some number, let's say 100, could put any number, and then you say I equals 1 to n, x of I equals this blah blah blah, and then you say 100 here. So what this does is it takes you to the line where you have the statement 100. It's like a loop only. Okay, in C it's called the go to line. So what it does is it becomes a loop, and this continue statement actually is not required, but you just write it for understandability that okay, you are continuing the loop, and after this what do you do? Once you reach this line, you go to 100 again. So it will keep doing that. Now we don't use it anymore, but if you have, let's say, 50 nested do loops, a do loop inside a do loop inside a do loop inside a do loop, no, 50 is a bit too much, but let's say you have 6 do loops. It's very difficult if you're reading a long code to figure out which do loop this end do was for the first loop, the second, or the third one. So sometimes, just for convenience, we put this nowadays also, so that the reader of the code can understand that okay, this is the end of the do loop that started here, because you have the word 100, and you have the next somewhere you have, let's say, 50. So the 50 is matching with the 50. So it's still useful nowadays if you're using many nested loops in Fortran. Conditionals, if else. So here again nothing interesting on the top. So here we are saying that if, so I has been made equal to 3. So if you have an if condition, now whatever the boolean the condition that we have is going to be put into parentheses. So the comparison that we are doing is if I is less than equal to 2, and then you have the word then, and then you print something. Then we can have an else if. So if this if condition is not true, it goes to the else, and then it checks another if condition. If I is not equal to 5, then it prints. So since I was not equal, less than equal to 2, so I is definitely greater than 2, but I is not equal to 5, so it says I is greater than 2 but not equal to 5. And if even this is not true, then it says that I is equal to 5. It's very random kind of a conditional that is there, but just to explain the idea of if else here. So you have an if, and you always have an end if, unlike Python again where you never had an end if. So with an if you will always have an end if, and you can also have many else if conditions and at most one else condition. Okay. Again, play around with this when you start running things. So logicals or booleans. In Fortran, in Python, we have a capital T, a true with a capital T or a false with a capital F. Here we have a dot true dot and a dot false dot. So if you have to have a logical or a boolean in it's a data type again, which can take two values, true or false. So you'll use this dot true dot. If you use something else, it will give an error. Comparisons are less than, greater than, less than equal to, greater than equal to. Double equal to is for equality comparison, and not equal to is slash equal to. So these are the new Fortran ways of using syntax, but you can also use the old Fortran syntax. In fact, I prefer that for some reason. It says rather than using less than, you say dot lt, less than, because the symbol is confusing sometimes when you're reading a long code. But if you see a less than, it for me it makes me understand things very easily. This is greater than, this is less than equal to, greater than equal to, or not equal to. Okay. So you can have, you can combine these logical statements. So this first if has a logical statement. So the complete logical will be inside parentheses. It says if I is greater than equal to 5, and then you want to combine two logicals, so use an and, a logical and, which is a dot and dot. Okay. And this ampersand symbol is actually a continuation character in Fortran. So what this means is that whatever is coming after this is whatever is in the next line is actually a part of this line. Okay. And make sure you remember this then in the if. Many times we miss it and then there's an error. Here's a code that uses the Boolean types, the logical types. So we have two integers I and k, and this time we also have a logical variable called ever underscore 0. So this can take two values, true or false, and we initialize that ever 0 to false, and then the code proceeds. So I'll let you figure out when you read the code yourself as to what it is doing. So make sure that you try to read and understand the code. Again, the code is not doing something amazing here, but it just is implementing some idea. Okay, so let's move on to the Fortran hands-on. So let me run it. If you feel comfortable, you can try things. I'll basically run whatever we have discussed in the class in the codes, the same codes. So they'll not be new to you. So if you want, you can proceed with me, or I'll give you half an hour to run these Fortran codes yourself. So let's take 10 minutes and try this out, and then we'll have a break, and then you can try things at your own pace. I'll also, after the break, I will put these slides on Moodle for your help. So by now you may have realized that you can continue to use the virtual, or if you want, you can use, or you can also use the core Ubuntu that's available on these desktops. So whatever is convenient. I am not using virtual machines anymore because I'm on a Windows machine. So I have installed a WSL based Windows subsystem for Linux based Ubuntu. So I'm using that, but whatever I'm doing, you can do yourself in a Linux machine as well. Same commands. So I have a Git folder here.
Sir, do we need to install its compiler in Ubuntu?
Sorry?
Fortran's compiler, do we need to install it separately?
No, G-Fortran is available on the virtual machine. Okay, so you can use that, but if you want to install that on your machine, you have to install it yourself. So on a Linux machine, you'll simply say sudo apt install G-Fortran, and then it asks for a password. I've already installed that. So that's pretty much what you need to do on a Linux machine or a Debian based machine like Ubuntu to install things. Can we switch off that? Can you switch off the light which says a P? It has a P on the top. Vishal, just switch off this light. Right. So we have the repository here. 24. If you go into the codes folder, you should see a Fortran folder now. So we go into that, and in there we see a folder called basics. So we'll separate. We'll have different folders depending on what we do, because we'll be using Fortran a lot in the course. And then we have these four codes. Example 1, loop 1, if else 1, and boolean 1. So let's have a look at example 1, the code. Okay, as I've opened the code in an editor called Sublime Text. It's a light editor. It allows syntax highlighting for languages such as Python, Bash. For Fortran, you have to put in some packages for highlighting languages. I like it personally. It's called Sublime Text. I've installed that. It's available for Linux, Mac, Windows, and so on. You can also use standard editors like gedit in Ubuntu if you want. Since I'm on Windows, I installed Sublime Text. So I'm opening the codes there, and on the side we'll have this terminal. Right, so example 1 is on the left. So the first thing we do is we type G-Fortran, and then we write example 1.f90. So that's the first way to do it without breaking into two steps. Sorry. When you do that, it has completed compiling. So if I do an ls -l, you can see there's an a.out now that's been generated. So the way we run this is we say /a.out, enter, and it prints z equals 4.2. So x was 4 and y was 0.2, so z becomes 4.2, and it uses some format. And again you can see that there is a 2 at the end, so that's your machine epsilon that is still with us. Next, if I want to give it an executable name, so let's say example 1.exe. So this time if I do an ls, it has generated example 1.exe. Let's remove a.out. So the way we run this example1.exe is the same, / example1.exe, and we get the same result. Okay, so that was one. The next thing I'll demonstrate is to break this compilation and linking into two parts, two steps. Let's clear and remove example1. Right. So the first thing we do is we say g4 and then the code. We only want to compile, so I'll put the -c flag. So when you do that, you see that it has generated example1.o. That's the object file. So now we will supply this object file. Then center. So again, since there was no name given, it links this object file and generates an a.out. So you run this using /a.out, we get the same result. Okay. And then you do the same thing for all other codes. If we look at let's say if else, so this is the if else code. So we say g fortran if else one and you do a /a.out, and since I is equal to 3, it says I is not less than 2 and I is greater than 2 but not less than 5. Any questions? So I'll let you practice by yourself now, so you can take a break if you want and come back in 5 minutes. In the last half an hour, I'll talk about debugging Python codes, particularly the use of a Python debugger called PDB. So let's take half an hour. I'll move around and make sure you try out Fortran today yourself.